Okay, so today we will start to talk about the area 2 related to sports. So my name is Ming Zhang, Chair Professor of Biomechanics, Head of Department of Biomedical Engineering, and Director of Research Institute for Sports Science and Technology. Now, in this program, we try to talk about, we have several areas. Okay, the first is food and nutrition, second is sports, smart aging, mental health, sharp vision, Chinese medicine. So last 2 weeks, you learned something related to food and nutrition. Now, after you got enough food, what we should do for a smart living or healthy life? We should do sports. So in the coming 2 weeks, we talk about latest development, advancement in sports science and technology. So next week, we'll talk about health benefits of running for chronic disease prevention. So we take a very popular sports exercise of running. Okay. So we'll have 4 lectures for these 2 weeks. So include myself, then Dr. Kenneth Zheng, and Dr. Jason Zhang, and Dr. Matthew Tan. Okay, now let's start talk about sports. When we talk about sports, we also should include physical exercise. Now, what's the difference between sports and physical exercise? Sports is a special type of competitive, rule-bound physical activity or game for entertainment, skill development, and the tournament. That means you have to get who will be the number 1, number 2, number 3. Okay, and sports may provide enjoyment to participants, also entertainment to spectators. So when we talk about sports, I think we will think about Olympic. So the Olympic Games provide a lot of opportunity for people to join the game and also get the entertainment from the game. So Olympic have a motto, fast, higher, stronger, together. So that means we will try to be the top of the people. We have to be the fast and to be the highest, stronger. Physical exercise is any planned, structured, and repetitive physical activity performed to improve or to maintain health and fitness without necessarily involving competition or rules. So for the general people, we do physical exercise, not only sports. Okay. Now, why should we do sports or physical exercise? Definitely, we got the benefit for our health and our well-being. So we often say, sports can strengthen musculoskeletal system. Okay, I try to put. Okay, so sports can strengthen our musculoskeletal system to make our muscles strong, to make our high bone density, to make our joint more flexible and strong. Second, to improve our cardiovascular health and the immune system. So to enhance and our metabolic health and to manage the body weight. That's very important, okay, to control our body weight. To reduce the risk of a chronic disease or chronic condition. So what is a chronic disease? What is a chronic condition? I will mention that later, okay? So try to release the stress and anxiety. Too small, the pen. Okay, so we can release our stress, anxiety to improve our quality of sleep. So that means sports can make people happy, can make our fitness and well-being. Now, actually, nowadays, many people may not do sports properly. We call that physical inactivity. Physical inactivity increase the risk for non-communicable disease and for other poor health outcome. So for example, people like to lying on the bed and sitting, and particularly nowadays we have the mobile phone. So play the mobile phone all the time. So people stop the movement. We call that physical inactivity. Okay, does move. Sorry. Okay, so if we go to the WHO, World Health Organization, there are recommendations for regular physical activity for different target of people. Now, for example, for children or the young people aged between 6 to 17 years old, and the recommendation will be all children, adolescents are recommend at least 60 minutes daily physical activity. So the longer, the better. Okay, the physical activity should be primarily aerobic nature and intensive and moderate and to high. And for the adult, normally for adult age from 18, and recommend to be do physical activity at least 150 minutes a week at a moderate intensity. For the elderly, if the age are larger than 64, the same recommendation for the adult at the same time should have a muscle strengthening exercise and at a high velocity if possible. Balance training and individual for the individual with impaired ability should perform as much exercise as possible. So this is the recommendation from WHO. But actually, if you go to the WHO, they put the key factor there. Okay, the first, regular physical activity provides significant physical and mental health benefit. In adult, physical activity contribute to prevention and management of non-communicable disease such as cardiovascular disease, cancer, diabetics, and reduce symptoms of depression, anxious, enhance brain health, and can improve overall well-being in children. But actually, uh, uh, there are about 31% of the adult and 80% adolescent do not meet the recommendation of the physical activity. So that means people do not do enough physical activity, and that's called physical inactivity. So the global estimate of the cost for physical inactivity to public health care system between 2020 and 2030 is about 300 billion US dollar. That's a big cost if the level of physical inactivity are not reduced. Okay. Now, why not do enough physical exercise? So we all know physical exercise can benefit to our health and our our life. But why people do not do that? So there are some barriers or some concern. First, people say, I don't have enough time to do exercise. Second, it's not convenient to do exercise sometimes, maybe because of venue. Third, lack of the self-motivation, lack the confidence, not enjoyable. Okay, people may not like the exercise. Boredom with exercise. Important, people do exercise, they may feel tired and painful. The last one, fear of the injury. Sports injury is a big concern for some people. If we do not do properly, then we cause a problem. Okay, then we will cause a problem. So that's why we need to do research for sports science technology. So we need to understand the significance of the health and the benefit and to have enough motivation for the person to do the exercise. The second, normally people start to exercise is very difficult to persist in, and they may not do physical exercise properly. The last one, we need to do prevention and protection. All those should be guided by science and technology. So that's why we say we need to do research to make sports more interesting, more rewarding, and safer for everyone. Take a running as an example. We all know running is a popular form of physical activity. So we all believe proper running can benefit our feet and health. So if you see this diagram, it seems any of our organ or system will be benefited from running exercise. However, not many people get a benefit from running. So I take two main reasons. There are many other reasons, but these two may be one major concern. The first one, some people worry about the injury. For example, the knee tear and the knee wear. And many people say, if I run, my knee soft tissue will be well and disappeared, okay, or got the knee OA. Some worry about the knee injury. Second, it's very difficult to start, very difficult to persist in. So when people do sports, then difficult to persist, sometimes because painful. So can we make running to be safe, interesting, and effective to improve our health? We do need some research to help us. So now, I just mentioned nowadays there are many chronic conditions or chronic disease. Those include overweight, fat, okay? Hypertension, that means high blood pressure. Hyperlipidemia, that means there are too many oil, too fat, okay? And hyperglycemia, so that means a lot sugar. Hyperuricemia, and mental issue, sleeping difficulty, osteoporosis, all those we call that chronic condition disease. So this is caused by physical inactivity, okay? So if people got any one of those chronic condition, if you go to the hospital, normally the doctor will give you medicine. So myself is hypertension. So I need to eat a tablet every day, but I have a bigger concern whether the medicine give a side product or any side effect. Okay? Now we are thinking when we talk about medicine, that is called a medicine prescription. Can we do exercise? Nowadays, people talk a lot about exercise prescription. So if I say that is sports exercise prescription or intervention, so that include according to the age, gender, health status, physical fitness, and the functional state of our cardiovascular sports organ combined with subjective object condition, formulate suitable exercise content, intensity, duration, and frequency. And this sometimes we call that exercise prescription. So based on your condition, then the doctor will give you suggestion what type of sports you should do. Okay, so we need to also let the people know what is the precaution during the exercise to achieve the purpose of carrying out rehabilitation treatment or preventive fitness in a scientific or planned way. Okay, now how to do physical exercise prescription properly? We need support from our science and technology research. Now, because the importance of research on our sports in the future, I should say sports science technology play very important role in our physical exercise. And that's why PolyU formed a research institute called RI Sports 3 years ago. And this is under PAIR. So PAIR means our PolyU Academy for Interdisciplinary Research. And this research institute mainly try to understand sports science and technology. So we have an inauguration ceremony on 24th of Feb 2023. Okay, so we try to let people know we will do this type of research. Now, the purpose of the Research Institute for Sports Science Technology is to try to integrate PolyU experts. You know, PolyU has a very strong engineering technology department. A lot of professors work on this area. So we need to integrate those technology and to collaborate with the world leader to provide scientific and novel engineering solutions for sports. These are the purpose for our research institute, RI Sports. So we work for different type of people, for elite athletes, for general public, and the person with the special needs. For the elite athletes, we try to strengthen their competitiveness and the performance. So that's why we say we from science to medal. Let the elite athlete to get more medal in a scientific way. Hey, for the general public, we try to stimulate more people to do sports in a safe way for recreation and health. So very important is in a safe way. So try to avoid or reduce the injury of the body. For the person with special needs, for example, and the person with a disability, for the some elderly or some obesity person, so we may provide assistive technology and some new technology to allow them to sports therapy and rehabilitation. So we always say we will work together to make sports more interesting, more rewarding, and safer for everyone. So based on our expertise, we will research for under 4 research themes. The first one, sports biomechanics and human product interaction. The second one, sports product design, materials, and manufacture, since we have a very strong engineering faculty and the school of textile and fashion. So we will do some new product development. So the third one, sports measurement, feedback, and instrumentation. That's very important to understand our performance, also to understand our physiological response to sports. The last one is sports training and rehabilitation. You know, PolyU have a strong rehabilitation research, so we are trying to transfer that to elite athletes. And our research institute have a group of very top athletes to be our sports advisor. And those have 10, I should say, world champion or Olympic champion. They provide advice to our research institute. We also have a strategic collaboration with other university or institution. For example, we sign agreement with the Hong Kong Sports Institute, and we have a number of projects with Hong Kong Sports Institute. They have an elite athlete there. Okay. We also work with the Samaranchi Sports Development Center and the ABSG Sports Technology Talent Industrial Development Center. Okay, so even a high school, DGS school, and we have agreement to work together with them. So recently we have agreement with the Li Ning Sports Product Company. Okay. Now I give a very short video to show to using one sports to show what our research institute can do.
The Research Institute for Sports Science and Technology aims to integrate experts from PolyU and across the globe to conduct interdisciplinary sports science research. We have 4 research themes, and we're going to illustrate them by the example of tennis. As one of the top 5 most popular sports around the world, many aspects of tennis deserve further investigation. Sportswear innovations can enhance athletic performance. For example, moisture wicking technology in sportswear enables sweat to evaporate through spatially distributed channels, which helps to keep its users dry and comfortable during physical activities. Performance enhancement is one of the main purposes of research in sports biomechanics and human product interactions. Inertial measurement units can measure a body's angular rate and orientation, such as extreme joint angles and range of motion. Insole sensors can record plantar pressure distribution and its loading characteristics during movements. Analytics of joint biomechanics provides methods for athletes to improve their technique and performance. The prediction and control of ball flight trajectory are important for tennis success. Aerodynamic forces experienced by the ball are affected by many different factors, such as its speed and spinning rate. Computational fluid dynamics can be used to analyze the force generation mechanisms. Results allow coaches and players to predict the ball trajectory and fine-tune their training strategies. Sports recovery and fatigue management through methods such as cryotherapy or contrast temperature play important roles in athletes' well-being. Shear wave elastography can be used to quantify exercise-induced muscle and tendon stiffness, while autonomic nervous system activities during sleep can be analysed to evaluate sleep quality. More effective recovery strategies can then be developed to reduce fatigue and enhance performance. Let's work together to make sports more interesting, more rewarding, and safer for everyone.
Okay, so just a short video, try to using tennis as an example to show what our 4 themes can do, okay? Now, I will give you more elaborate what we are doing. Now, if you see the new science technology for sports and exercise, there are a lot of new technology. For example, science in biomechanics, ergonomics, computer science, AI, video assist reference, smart sportswear, functional footwear, fan engagement, esports, AR, VR. There are a lot of new technology here. Okay, wearable sensor, robotic, computer vision, 3D printing, digital design, data science, fatigue protection, a lot. And so the purpose for our research institute try to combine those technology to our exercise. And now the first one, let me give more example related to what we are doing. Okay, so the first one, sports biomechanics and the human performance interaction. So the most popular one, we needed to have the motion analysis. We can using different camera to get the video of the people. Then we can do further analysis, either do 3D reconstruction to get the 3D shape of the body. Then we can further analyze their performance. Or we can using computer vision or AI to transfer 2D video to 3D based on based on the new technology. For example, this is a 2D video maybe get from some game, and sometime the coach want to know the 3D performance. So that's why we can do this type of analysis. Example. So this is the fencing. Okay, so original is the video, then we can use a model. Then to get the 3D, this will be 3D model. Then you can get the movement of any part of the body. Okay, we also can using those video to do some state reconstruction and tactics. So for example, this basketball, using the video, we know the position of the athletes, then we can do the further analysis. And sometime we're thinking to do a AI sports lab, collaborate with some company. This is a device. So this device, you can see there are sensor here. When you do exercise in front of the machine will record the body, the movement. Then we can do the further analysis to see whether your performance is good enough. And I'm thinking in the future, PolyU should using this AI sports lab to let students do exercise without any involvement of teachers. Okay. Now, after video, we can do further biomechanical study to understand the biomechanics of a human. For example, we know the movement, then we can analyze the internal force, for example, the muscle force and the joint force. And then we know which muscle will be active, how large the force on the muscle, is there any damage caused. Further, we can use in computational model to analyze the internal stress strain distribution or combined with the shoe design, and we can see the interaction between foot and the shoe. Then we can know whether we design is good or not, or even the lying, sitting, or any type of movement. So the next one is related to product development. So for example, we have an aerodynamic in sports, so we can see the ball movement. Then based on the ball movement, we can see what are the resistance, and people can design a new ball based on the performance of the ball. So 3D printing is a new technology, and our team work a lot on those manufacture, for example, the new footwear insole. We can design an individual footwear or insole to meet a different requirement. For example, we can take the shape of the foot and the plantar pressure, the plantar shape of the foot. Then we can do the walking to see the individual performance that we can use in 3D to print or to design individual designed insole. Okay, so also using 3D to print those those basketball, those bicycle, etc. Okay. PolyU have a strong team in fashion and textile. They work a lot on sportswear, so they design packs of the materials to control the temperature, control the humidity, resistance, blood flow, oxygen, comfort, and the taste a lot, okay? A lot of functional materials and functional design for the sportswear. So the next part for the sports measurement and the feedback instrumentation. So we have a team work on fatigue identification because fatigue is very important during sports. If people got fatigue, it's easy to got the injured. So we need to know the situation. So we work on the gait parameter, heart rate, blood pressure, oxygen consumption, muscle activity, using EMG and muscle tissue oxygenation using NIRS. Okay, even other, you take the lactic acid. So all those can provide some information for the fatigue. And we also have a number of team work on the flexible biosensor, for example, sweat glucose analysis and some strain analysis for stretchable conductor. And even one team work on using the sweat to see our lactic situation, okay? And using some new technology. All those can let us know the situation of our muscle. And we also have a good researcher, Wang Xin, is Olympic champion 2008 in Beijing. And he is a 10-meter diver. And he tried to, using our technology, to measure the takeoff. and to see the flying, and also to measure the pressure between water and the body, because the high pressure may injure our body. So you can see this jump, and we can do the analysis to the muscle force. We can do the computational model, and then we can see all the interface. But anyway, and Wang Xin tried to using our engineer technology to understanding diving. And we also have a team work on the swimming using the sensor to measure the force, to measure the movement, to measure the muscle activity. Also for the cycling, okay, to know what are the power and the rotation, the muscle force, etc. We have also worked on 3D full body shape and the database for health. You know, different people have a different shape, different dimension, different situation. So we try to develop a device can quickly record the body shape. Then we know the dimension for our body. We know and all the girth, the lungs, even the body shape to see the fat situation and the shape of the body. And sometimes people got some potential problem because, for example, scoliosis and some curved leg for the O leg, X leg, and flat foot and high arch foot, etc. So we can using our technology quick do the body check, give any potential problem. Then if the people got a very severe situation, we will recommend to see the doctor. Otherwise, we can suggest some supports or special body support to solve some problem. Okay, so running very important. I mentioned that we have a team working on a type of called Tai Chi run. Okay, some people like to run very fast. Sometimes people like to run very slow. So this is an exercise I have done for 2 years. Okay, start from a very slow running, then gradually increase the speed, then to the certain level, gradually reduce our speed. And we will measure our heart rate and control the heart rate. Some people can get very high, sometimes people got very low. So for example, in my age, I will control my heart rate lower than 140 something. For young people, you may get close to 200, no problem. But for elderly, even lower. So we need to control that. We make sure there are no damage or no hurt to our heart, our blood system. Okay, and then we can reduce the speed. People will feel very relaxed after running. So this is a type of running we are doing. Okay, then we have a Tai Chi run game for 2 times, and we have some golf time. Okay, the last one related to sports training rehabilitation. So we have a team work for the Paralympic athletes. We know Hong Kong got a very strong team for Paralympic game. They get a lot of medals, and we provide service for them for prosthesis, for orthosis, even chair modification, etc. Now, PolyU doing form the research institute for sports science and technology, mainly for research. So we also set up a new program for sports science technology. Start from this year, we have a Master of Science in Sports Technology and Sports Management. And the quarter is 60. So we got 60 every year. And those are the subject we are taught. So we try to put the new technology to sports science. And also we put a stream on the BME program called Sports Science Technology from this year. So from next year, we will have an independent program called BSc in Sports Science and Technology. So for the local quarter will be 20 plus 10 senior year plus 40 international student. Okay, so we have a new program. We also PolyU also set up scholarship for undergraduates, for TPG student and RPG. And if you are very top elite athletes, if you want to get a bachelor degree, master degree, or PhD degree, PolyU have a lot of those scholarship. Now, Wang Xin is supported by RPG students in PolyU. Oh, sorry. So last year, we have a symposium on sports science technology. At the same time, we form a new society. So the society called International Society of Sports Science and Technology. And if you are interested, you can scan this QR code to join our society. So the mission of the society to foster collaboration among researchers. So not only Hong Kong researcher, also mainland, also over the world. Okay, and the society will organize the conference. The conference will be at the end of this year. So that means in November 29, we have a new forum on innovation technology for sports development, and also a welcome reception for the first World Congress on Sports Science Technology. This is at 6 to 8 o'clock at the PolyU Logo Square. So if you are interested, welcome you to join. And we will have the first World Congress on Sports Science and Technology and in 29 November to 2nd December. If you are interested in our conference, you can scan this QR code. More information can be get there. Okay, I using more than half an hour, just give you a brief introduction of sports and exercise, particularly what our Research Institute Sports Science Technology is doing. And the following, I will give the time to Dr. Kenneth Zheng, and he will talk more about sports science technology. And the next lecture, we will take a running as an example. Okay, I will thank you very much, Kenneth. Give time to you. You mute.
Okay, sure. Maybe we can take a quick break now, before maybe around 5 minutes. So can the students just be reminded that we have some multiple choice questions that have been uploaded onto Blackboard. So after the lectures, please remember to go to Blackboard to do the MCQs to see whether you understand the knowledge that I'm going to talk about in the second half of this seminar. So we are going to take a 5 minutes break, and we are going to resume class at 7:15. Okay, so it's time to resume class. So today I'm going to give a talk on the technologies for sports performance and injury assessment. So yes, running is definitely one of the examples that I'm going to use, but like I'm also going to talk about like sports in general, because like there will be another lecture next week that will be focusing on running. So actually, like sports technologies can be used for many different purposes. Traditionally, it has been used for performance evaluations because it's very important for not only the athletes themselves, but also the coaches to understand their own performance. Because without this knowledge, it will be very difficult to elevate their performance and to allow them to run faster, jump higher, or be stronger when they're doing lifting sports. So also like sports technologies is also used for designing new training programs, because if you know, like sports has developed very quickly since the last 2 decades. Like 2 decades ago, like when Max Spitz won 10 gold medals before in the Olympic Games, like his time was actually like 10 to 20 seconds slower than Michael Phelps when he broke the world record in the Beijing Olympic. If you just look at the physical body, like actually like they are not that different. Like they have very, very similar physique, but then like is quite tremendous improvements that they are able to strip around 20 seconds off the best time. Because if you are not familiar with swimming, like if you can swim 10 to 20 seconds faster, that is almost like 25 meters to 30 meters apart. In a standard size 15-meter pool, like there's almost like half of the pool, which is tremendous. Like if you are looking at sports, like if you win by like 20 seconds, like you are winning by a landslide. So a lot of that is due to the advances in different sports technologies, including the sportswear, but a lot of it is due to the development of new sensors and devices so that we can actually monitor the athlete's performance and to design new training programs to elevate the games. Also, sports technologies is used for competition analysis and tactics. You see a lot of those in, for example, like real-time streamings of sports events that you can see the player statistics, not only very simple statistics like how many points they score, but also like how the plays develop in the games. Like there are lots of new technologies that are being used. For example, VAR can also be used into determining whether a player is offside or whether a ball entered across the goal line in soccer. And of course, sports technology is used a lot in sports injury preventions and rehabilitations. So a lot of the new technologies have gone into this area because in sports, not only the main goal is to elevate the games, but also to do it safely and to restore the physical conditions once someone is injured. So a lot of time, the sports technologies invested into this area. And finally, of course, like sports technologies, there are lots of advancements in both the research and also equipment advancements. So there are lots more newer sports equipments that are being developed. For example, due to the advances in different materials, a lot of time now, for example, the racket sports, they put a lot more composite materials, for example, carbon fibers in the materials that traditionally has been used using metal or using wood. And having composite materials, it has a lot better material properties that allow the athletes to elevate the games by using better design equipment. So I'm going to talk about different areas of sports technologies that have undergone a lot of development over the years. And one of the first one is motion capture analysis. Because a lot of time when we want to study sports movements, like we need to capture what the person is doing. By having the knowledge about the movements, then we can then know how the movements are, what the movements are they are performing, and then what improvement that we can make based on the existing movements. So in terms of motion capture analysis, there are a few main different areas. One of them is using marker-based motion capture. So we have cameras around the room, and then we can capture the reflective markers that are being placed around the subjects. Usually, these markers are being placed on important bony landmarks so that you can see that in the image next to it, we can have the skeletal model of the person. Another type is we can attach some sensors along the limb segments of the athlete. And by doing so, these sensors are specializing in detecting different types of movements, for example, linear motions of the body or rotational movements of the joints. And by having this data, we can also be able to capture the motions of the body. And of course, if you want to really understand what's going on within the body, then having the sensors on top of the body or by having reflective marker being placed on body are not sufficient because you will not see how the bone and muscle interact. And because of that, there are some motion capture systems that are specializing in actually capturing the motions of the inner structures of the body, for example, the bones and the joints, and how they interact during sports. So the first type of motion analysis that I'm going to share with you would be a optical-based motion capture system. So these type of systems are widely used in sports, and they are considered the gold standard because of their high sampling frequency and also high spatial resolutions. For these type of systems, usually a spatial resolution is less than 1 mm, so you can have very, very accurate data. The next type of system that I'm going to share with you will be using inertial measurement unit or IMUs. So this type of devices, you can see that the athletes are wearing these orange sensors around the ankle. These sensors are specializing in detecting the linear angular motions of the body. And finally, dual fluoroscopies or X-rays can be used to capture the 3D images of the bones movement during sports. If we look at the optical-based motion capture systems, this can be further divided into both the marker-based and markerless, and both have the pros and cons. For example, for the marker-based, usually it excels in having better data accuracy, whereas the markerless is usually used when we want to have maximize convenience, because we don't need to place anything on the human body when we capture the motions. So this is an image of the marker-based motion capture systems. You can see that the athlete would be wearing a lot of reflective markers along the body. And the cameras will be placed all the way around the room. And by knowing the positions of these reflective markers, then the computer algorithm will then be able to reconstruct the 3D coordinates of the different body segments, and hence we can then know how the person is moving in the space. So a very brief sample of how the technology works is we can have multiple cameras being placed around the users. Usually, depending on the space that we are working on, then we can have more or less cameras. Usually, the minimum number of cameras we need will be 6 cameras, because we need to have at least 2 cameras looking at the same marker at the same time in order to register this in space. Because if you have only one single camera, then this marker will not have sufficient information to be translated into the 3D positions. So if the space is relatively small, for example, if this is around 6 meter by 6 meter dimension, then usually we can go away with around 6 to 8 cameras. But then if we are working in a big stadium or a basketball court or a soccer field, we need a lot more cameras, and that's why it's going to be, the cost will be tremendous. And that's why most of the time, we will when we're using these type of systems, the area of interest is usually smaller, usually within the room. And they are actually, even though they are marker-based systems, but then there are 2 types of markers that can be used to capture the motions. A first type of marker is called active marker. So active markers, you can see that when the markers are being placed around the body, these markers are actually powered by electricity, and then this can emit infrared signals. And each markers, even though when you look at them, they all appear to be red, but actually the frequency can be slightly different, so that when the marker pick up the reflective markers, they can automatically know which marker correspond to which joint. For example, they will find that, oh, this is marker number 7, this is marker number 8, because there's some slight variations in the frequency of light that's being emitted by these markers. Whereas for the passive markers, basically we are placing styrofoam balls onto different parts of the body. Usually they are around important joints, for example, the elbow, the wrist, or the hand and the fingers, and also the hip, the knees, and the ankle. And by having the markers on the surface of the body, we can use different mathematical models to estimate the location of the joint centers. But then the problem with this, the pros of this type of marker is that the location of the markers can be quite flexible. We can place them basically anywhere. And then as long as we have the model to translate the marker positions back to the joint centers, then that will be good. So sometimes when we need to do very gross movement, then a lot of time we don't need that many markers, because all we're interested in will be the location of the big joint center, for example, the elbow, the shoulders, and the wrist, etc. But then if we want to look for very delicate movement, for example, movement of the ankle joint or how the foot is moving, a lot of time we can place just 20 markers just around the feet, because we want to see the subtle movement of the foot. Or if we want to capture facial expressions, we can place 20 or 30 markers just on the face themselves. So how we place the markers really depends on the applications that we are using and the model that will be used to analyze the data. But the problem with this passive marker placement is that because the markers are basically just styrofoam balls with reflective tapes being taped onto the surface. So the frequency that it can reflect would be identical. So the systems will not be able to differentiate the light that's being reflected by the solar marker compared to the light being reflected by the elbow markers. So they all look the same to the systems. So we need to do extra steps in the post-processing to tell the systems like which marker correspond to which joint, and that can be a very time-consuming process at some time. So that are the two main markers. So how does the cameras actually identify the 3D positions of the markers in space? So you can see that there are multiple cameras being placed around the room. In this image, there are 1, 2, 3, 4, 5, 6, 7, 8 tripods, and on each tripod there are 2 cameras. So there are actually 16 cameras already placed around the room. And for this type of systems, the camera is not only capturing the image from the area of interest, but also they are emitting infrared light into the area. And when the styrofoam balls is being struck by the infrared light, they can reflect back, and this reflection is being captured by the cameras from different angles. As you can see, the cameras can see the markers that are being placed in front of them. The back markers will be occluded by the body, so you cannot see the markers on the back side of the body, for example, just like how the human eyes are working. So, for example, in this image here, you can see that camera 1 can see these 3 markers: marker 1, marker 2, marker 3. Just like camera 2, camera 3, and camera 4, all of them can actually see the 3 front marker. But if a marker that can only be seen by one camera, and then at the intersections of this point, then by knowing the camera orientations and how these individual points on the image, then we can be able to reconstruct the 3D positions of the marker. But this can only be possible if more than 2, if at least 2 cameras can see it, because we need to have the intersections from the camera images in order to know the 3D positions. If only one camera can see a particular marker, for example, if camera 1 can see this marker, but all the other cameras cannot see it because the board is blocking this view, then we only know that this marker is showing up at a 2D pixel coordinate on this image. But because we do not have a second camera that can verify the other positions of this marker, it is unable to reconstruct the 3D positions. So that's why sometimes when we use optical-based systems, the occlusions will be a main problem, and sometimes we will lose some important data if we do not place sufficient number of cameras around the person to capture sufficient images. Because if the image is, if a marker is only seen by one camera, then that marker may does not register to the system, and it will be lost. So by placing the markers onto the skin, and then when the markers can be captured by the cameras, and if the markers can be registered by at least 2 cameras so that we can find intersections of these images, then we can actually reconstruct the locations of each of these markers. And as I said before, like this image that you see is already after post-processing. Before we process this data, all this image is showing is just some white dots on the screen, and you will not be able to tell whether this will be the hip joint, the knee joint, or the ankle joint. So actually, before we get to this image here, we actually need to tell the systems what are those individual markers. For example, this will be the right side of the front hip, this will be the left side of the front hip, and this will be the right side of the back hip, and this will be the left side of my back hip. And this will be my knee joint, this marker will be on my thigh, etc., and etc., etc. So I actually need to tell the systems which marker correspond to which. And as long as they stay visible throughout the data collection process, then we only need to do this process once. So it's actually not too bad if you have sufficient number of cameras. But if you only have very few cameras, occlusions will cause a marker to jump in and out from frame to frame, and then we may need to relabel this the marker, and it's going to be a time-consuming process. So that's why these systems, although it's a gold standard, it also require a lot of processing and also a lot of cost, because you need to have many cameras in order to have good data from this system. So this is a video showing how we collect this type of data. So we can see that we can place multiple markers on the person. And after we place the markers, we will be able to track all the different body segments moving in space. And by doing so, we will be able to analyze very in detail, like how the person is moving. So we can do this in many different types of sports. We can do this in lawn bowling. We can do this in baseball. Not only we can capture the motions of the human body, but we can also capture the motions of sports equipment. This type of technologies has been used not only in sports, but also in clinic, where sometimes people may have different type of gait problem, so that we can analyze the movement and to have further understanding of how the problems of their gait, and then we'll be able to correct them. So these type of systems can be being used all around the world. So in all the major universities and lab. Oh, you can see that there's a missing marker. So they can see that the back sometimes is fresh in and out. That is the example that I was talking about. Sometimes the markers are being occluded, and that's why it's not being registered by the system. So you can see the markers being fresh in and out of the systems. But you have sufficient cameras, then usually there's not a major problem. But if you only have a few cameras, for example, in this lab, I can only see around 6 to 8 cameras, and that's why you will have some occlusion problems, and markers will jump in and out of the view, and sometimes you have some missing data. So with the marker-based systems, we can then, because by placing the markers correctly, we can actually sometimes be able to map where the skeletal is located within the marker. So by having different type of models, we can then be able to calculate what will be the joint angle at different phases of movement. For example, when during gait, they can look at what will be the joint angles at heel strike, at foot flat, at mid stance, at toe lift, etc., to see the entire gait cycle and to analyze the movement. So from these type of systems, not only that we can get very reliable kinematic data, but we can also get the orientation of different joint segments, the velocity of different joint segments, and the accelerations of different joint segments. And not only the linear kinematic variables that we can capture, we can also obtain angular movement, for example, the joint angle and the joint angle velocity, etc. So those data can be easily captured using optical motion capture systems. So you can see that a lot of famous athletes have been used when we collect our data from different, when we try to analyze different sports. And sometimes like they are actually not in the lab for us to analyze their movement, but a lot of time they are paid to get their movement captured by video games company. As you can see that here, Electronic Arts, EA, is a big company to make different sports video games, and also the 2K systems are also very famous in making basketball games. So you can see there are lots of famous athletes here, and I'm sure that you can recognize most of them. For example, Kobe Bryant here, and then we have Steph Curry back here, Kevin Durant down here, and down below we have two of the biggest soccer stars, like the GOATs of soccer. We have Lionel Messi and also Cristiano Ronaldo from soccer. And on the top, you can see two very famous tennis players, both in the male and the female tennis world. We have Roger Federer and also Serena Williams. So those were the top two athletes in tennis. And so maybe you are not as familiar with this athlete here, but like this athlete is one of the most famous MMA athletes, McGregor. So he is like one of the top MMA athletes specializing in martial arts sports. So motion capture systems, as you can see, like unless we can get the athletes to come in the lab to capture the motions within the lab, if we want to capture the motions when the athletes are playing in the game, like we cannot expect ourselves to place markers on them and they have like a lot of cameras capturing around them, because like to capture this in an outdoor environment, first it will be very difficult because we need to have many cameras if we have a very large capture volume, and two, like it's impossible to place markers when the players are trying to compete in a game. Like they won't even allow it because you will feel discomfort and they won't tolerate that. And finally, there will be some technological limitations, because the marker-based systems is based on capturing the infrared light reflected by the markers, or the infrared light being emitted by the active markers. So, but then in outdoor environments, the sun would be the greatest infrared emitter. so that you will have a loss of noise, and the infrared light will sometimes be reflected not off the markers, but also out of the body or the clothing, etc. So it will be impossible to use a marker-based system in outdoor environment or in a real sports environment. And that's why we are moving into the next type of technologies that we have in sports, is the markerless systems. So in markerless systems, the type of devices that we capture the motions can be actually quite simple. A lot of time we will rely on the typical RGB cameras, or the red, green, or blue, or just regular cameras. So these cameras can be what we use or what we can commonly buy in our local camera stores. So digital single lens reflective cameras, or some specialized high-speed cameras that can capture 300 to 1,000 frames per second. So normally our regular cameras can typically capture around like 30 to 60 frames per second. Nowadays, some of the higher performing cameras can capture 120 to 230, 240 frames per second. For sports, sometimes that is actually not sufficient. For example, if you are trying to analyze golf, if you're just capturing at 200 frames per second or 240 frames per second, a lot of time you're going to miss the moment where the club head just strike the ball, the moment that you strike the ball. So you need to have very high-speed cameras, sometimes like 300 to 1,000 frames per second. But of course, like depending on the type of movement that you're analyzing, if you're just analyzing basketball shooting, for example, like even smartphone cameras can do, like with the resolutions and the speed that it offers. And if you want to have relatively high performing data, sometimes we will need to have multiple synchronized cameras from different fields, very similar to what we talked about earlier with the optical-based systems. If we can have multiple fields capturing the same movement at the same time, then we can do some rendering and also some 3D motion reconstructions to find the 3D location of different joints. And then we can then be able to reconstruct the 3D motions and analyze the body motions in all three planes. And that also often requires some AI involved, because we need to have some deep learning based algorithm to detect body key points, because we don't have the reflective markers there to tell me, oh, this points with my shoulder. So to the systems, they will only see the contour of the body, and the systems need to be very smart and identify within this contour where will be my shoulder, where will be my elbow, where will be my wrist, etc., so that you can actually reconstruct the entire body. And besides having some regular video cameras, we can also have some specialized cameras called depth sensing cameras. So these depth sensing cameras, besides having the video images, it can actually tell the distance of different pixels away from the camera center. So instead of seeing this video image of the person, is actually returning the distance of each pixel that is away from the camera center. And by having that, then we can have the rough idea of how far each body part is away from the camera center. So there are many commercialized cameras out there that are specializing in measuring that. For example, the oldest and most famous one would be Microsoft Kinect. If you're young, maybe you are not even aware of it because it's already discontinued. So nowadays, people are now using Intel RealSense or the OPIC Astra. So those are the newer systems that are specializing in detecting the depth images from the camera. So the depth sensing camera, usually we have the depth sensing camera sitting in front of the person when they do sports. So as you can think, the depth cameras can only see the front. So you can see that for each pixel was the 3D distance from the front of the camera, but you can never see the back because the light cannot travel to the back side of the body. So you can only see one side of the body, but not the back. So there will be some limitations. And also the depth accuracy will decrease with distance, because when the person is moving further away, the data will become unreliable. And also sometimes you can't even capture anything when the person is too far, because you have been too far away from the operating distance from the depth sensors. And a lot of time the field of view is also narrowed compared to regular red, green, and blue cameras, because you can only detect a relatively small area. We cannot detect the depth of every pixel that is very far away, on not just in the forward and backward distance, but also in the left to right distance to the cameras, because it has a limited field of view. And also, this type of systems usually have relatively slow frame rate. This type of cameras usually they will capture at most around 30 frames per second. Most of the system they do not capture anywhere over 30 frames per second. And if you have a very crowded image, sometimes the frame rate will even drop further. So that if you are trying to analyze sports, that may not be a very good idea, because as I said before, if you are trying to analyze golf, for example, even 300 frames per second will be too slow. So 30 frames per second will definitely be like snail speed, and you cannot capture any of the important moments in sports. So some systems they include a hybrid mode, so you can capture both the video images and also the depth images at the same time. And algorithm will be included to combine the two together, so that you have both the video images and also the depth images at the same time. But again, like there are lots of limitation, and just without markers and without a fast systems, like usually the application in the sports will be limited to movement that are relatively slow. So there are many different type of motion capture system that doesn't rely on markers. In the old days, they used a structured light system. So the light projector is, instead of projecting just infrared light in general, they will project strip of light. So when the strip of light hit any 3D objects in front, depending on how the light is being bent, then the cameras can then capture this image, and according to how the light is being bent by the object, then it can then reconstruct the 3D shape of this object. So this type of technologies was first used in capturing very static motions. For example, in fashion and textile, when the when the fashion designer want to have very accurate 3D measurements of the model, then they will use this set of technologies, because you can just send the light, and then by looking at the curve of the light on the person's body, then you can then have quite accurate 3D data of the surface of the body. But then, as you can see, you can only capture one side of the body. You don't know what's the how the body is shaped on the back side, so there will be some limitations. So sometimes you need to have multiple systems, or you need to have the system that's rotating around the body in order to capture the back side of the body as well. And also some newer systems would use time of flight or infrared pulse. So you will analyze the time that it takes for the light to bounce back from an object to calculate the depth. So you will emit the light, and then when the light bounces back, because we know that the speed of light is 3 times 10 to the 8th meters per second, then we will know how far is the object away from the emitter, and then we know the distance and or the depth data from the depth camera. And also stereo visions is sometimes used. So you have similar to the Vicon system, similar to the optical-based systems, you have two cameras looking at the image at the same time. And by having the two different view angles, the newer AI technologies is able to merge the images together to form the 3D data as well. And for that, you will need a lot of deep learning algorithm, for example, computer vision technologies, in order to train to identify humans and accurately predict the from the 3D positions to reconstruct the 3D position of the body. And we can do this as long as the multiple cameras are synchronized, then we can reconstruct the body movement in 3D throughout the entire movement. So you can see that these images is actually being used in sports, and you can identify various key features. For example, in baseball pitching, you can see that you can relatively well identify the shoulder, the elbow, and the wrist, etc. But then you can see that for the distal segments, for example, the wrist and the hand, a lot of time the accuracy will be limited. And also, like, if you want to see the detailed movement of the fingers, it's totally impossible. It's too far away, because due to the resolution of the cameras, you can hardly see the fingers being separated, and hence, like, there's nothing that the cameras can do. You can basically identify the big joints. So to date, like, the technologies to capture the large joints are actually quite mature. So we are able to capture it even with just one single camera, relatively accurate data of the large joint. But then, of course, like, this is nothing compared to the previous system that I talked about, like the optical-based system that are using markers. That is still the gold standard. Like, the error of them is like a sub-millimeter error. But in here, the error will be in the centimeter range. So you can see that within a more confined space, we can actually capture the movement of even individual fingers. But you can see that, like, most of the time it's doing quite well, but you can still see some glitches. Like, some of the time, like, the fingers was popping in and out of place. That's not where they are supposed to be. So there are still some limitations to the system, like, because the quality of data really depends on the video images that you collect and how well you can actually see all the body features from the cameras. So but then, yeah, we are making a tremendous progress in this area. Hopefully, in the future, with better cameras, with better resolutions, and better computer algorithm, we'll be able to correct all these little glitches and be able to avoid, like, the thumb jumping around, even though from a human eye, we know that the thumb will not be suddenly elongating and flipping in and out to some weird positions. Like, so some smarter AI will be able to detect that and correct those problems in future. So this is a type of commercialized markerless systems. You can see that the person is just dancing in front of the camera without any markers being placed on them. But the computers can actually detect all the joint locations very well. You can see that the hip joint location, the knee joint, the ankle joint, along with the shoulder, elbow, and wrist, like, you can see very relatively accurate data, no matter how the person is moving. Even when the camera sometimes may not even see the limb segments, even you can see that when the person has turned the body to the side, the computer algorithm can be able to estimate the locations of the limbs that is far away from cameras. So they can see that on the reconstructed image on the top right, is actually represent the movement, but actually extremely well. So these systems is getting more mature nowadays. So, but the problem is the processing speed sometimes is also quite slow, and also the amount of data being collected is also very large. So sometimes, if you need to process a lot of data within a short period of time, there will be a lot of computational issues. But then with faster computers, I'm sure that, like, we can solve this problem, like, in the near future. So for less sophisticated systems, so this is basically one single cameras, and then using some simple computer algorithm like OpenSIMs, we are able to track most of the large joints, for example, the shoulder and the elbow. But then, as you can see, like, you can track it relatively well if the person is more stable and if it's just facing in front of the camera. But then once the body is turning, or if the person is moving too quickly, a lot of time you can see that the marker cannot be tracking reliable. You can see that, especially for the smaller joints, for the ankle joint, you can see that it can be shifting quite a bit, and it's not even at the joint center a lot of time. And sometimes, due to loose clothing, it is also not able to detect some of the proximal joints. For example, the shoulder and the hip is greatly affected by the clothing that the person is wearing. Another problem with simple single camera systems would be when we have too many people. So you can see that when the person is wearing white suddenly move in the screen, it merge with the person in the back. So you can see part of the body is being tracked on the person wearing white in front, and then the arm will still track the person in the back. So sometimes the systems will not be able to identify multiple targets, especially when they overlap each other. So you can see that a lot of problem is also happening when the two girls on the right are trying to shake hands. So you cannot really tell where the wrist joint ends, and hence there are lots of errors in this area. So looking next, okay, so if we are really interested in capturing the motion of the body, and if we want to do this outdoor, like if we don't want to do this in the lab, and if we want to have more accurate data, what options do we have? So the next options would be to wear IMUs onto different body segments. So these are some wearable motion capture systems. So you can see that we can just wear relatively small devices around different joints, and then we can capture motion data from them. So maybe some of you may not come from the technological background, so you may not be familiar with what IMU are. So IMUs are actually some electronic devices that are specializing in detecting different type of motions. One type of devices are called accelerometers. As the name suggests, they are specializing in detecting linear motions, and they can detect linear motions not only along one single axis, but you can actually detect linear accelerations along three axes. For example, forward and backward, left and right, and also up and down. So they can detect all three lines of accelerations. And because we all know that gravity is also a form of accelerations, so you can also detect the line of gravity using accelerometer. The second type of electronic device that we will use in IMU would be gyroscopes. So gyroscopes are now installed in all cameras. So basically similar to accelerometers, but gyroscopes detect rotational movement along about all three axes. So you can detect rotation movement about the x-axis, about the y-axis, or about the z-axis, or the roll, pitch, or yaw. So you can see that all of the smartphones already have that, and that's why when you turn your phones to the side, your image can also turn to the side, so it knows that you're flipping your phone from a in a vertical directions into the horizontal directions. So from a what's the word? It just slipped my mind. In a from landscape, you can go to the portrait. Yes, the portrait view of the cameras. So those are the two types of devices that can detect both linear accelerations and also rotational speed. Finally, the third type of devices that we usually put within IMU would be a magnetometer. So these type of devices are used to detect the magnetic field of the Earth. So you can then tell what is the north directions of the device. So when we combine all three devices, basically we can then know the orientations of each of those IMUs, and also how fast each IMU is moving, both linearly in the linear accelerations, and also with the angular velocity of each of those devices, and also how they are aligned to the Earth's magnetic field. And having all these three data together, then we will be able to piece together the 3D orientations and kinematic profile of all these devices. And when we have multiple devices, one on the thigh, one on the shank, one on the forearm, one on the arm, one on the hand, for example, then we will be able to distinguish the relative movement of the different body segments. And from those data, then we can reconstruct the 3D position of the body. So as I said before, from the accelerometer, we can have very accurate 3D linear acceleration data from here, and also measure the gravity when it's in status. And for the gyroscopes, we can get accurate 3D angular velocity data. But then for this type of data, a lot of time drifting will be a problem. So for those who are not in the engineering background, what is drift? So drift is normally when we have a sensor that is being placed in a static position. So we are not moving the sensor. We expect to have a flat line, so that because the sensor is not moving, so the data should stay flat because there's no motion. But drifting is, even though the sensor is not moving, the data is slowly drifting downward or upward, thinking that, oh, the sensor is moving very slowly at a constant pace most of the time in one single direction. So that is a major problem, because we would want our sensor to tell me that, oh, the person is not moving when the sensor is not moving, but that's not the case. So how do we correct that? We actually need to use data from both the accelerometer and also the magnetometer. Because if we have the true north reference and also the line of gravity, we will know the orientation of the sensor. We know that whether it is actually rotating or not relative to the environment. And by doing that, we can actually correct within the IMU themselves to know that, oh, this is actually only a drift. This is not the person moving very slowly or rotating very slowly. So that we'll be able to get good accurate data from the IMU. It's because we have other systems other than just the gyroscope itself. We also have the accelerometers and also the magnetometers to correct for the drift problems. And that's why we have the fusion algorithm to combine data from all these three devices within IMUs to correct data from one another. So IMUs had lots of different applications in sports because we can basically put the sensors onto different body parts. So most of the time when we are doing running or walking studies, we will place one IMUs on the back, one on the thigh, one on the shank, and one on the foot. The reason why we do not need to have multiple sensors on the same segments is because they will be sensing the same thing, because we will treat different body segments as a rigid body when we use these type of systems. So by having sensors on different parts, then we can sense the relative motions between sensors, and then we'll be able to reconstruct the motion. So you can see that when the person is running on a treadmill, we can also detect the movement of individual IMUs that's being placed on the foot, on the lower leg, and on the thigh. And hence, we can see how the person is actually running in 3D space. And this data is coming from the force plate that we are going to talk about later on. So we are going to discuss this in a later slide. So the type of data that we can retrieve from IMUs are actually very similar to the optical-based systems. We can get the kinematic data and also the angular movement data from the joints. So we have the joint angular movement and also the joint angular velocity movement data. So moving next, if you actually want to know what happens within the body, then we can use dual fluoroscopies or X-rays from two different planes or dual planes to look at how the bones are actually moving underneath the skin. Because on the surface, even though you can see that the previous system, the THEA data, we are able to model how the bone is moving. But this is only a model, but not how the bones are actually moving. So we actually need to use X-ray from two different planes to know for sure like how the bones are interacting with each other and whether the bones are tracking properly. For example, whether sometimes in running, the patella may track incorrectly. It may track too far to one side or the other, causing knee pain in running. And sometimes if we need to understand further like what's happening to the person, then we will need to have X-ray images of the persons in sports. But then, as I said before, if you only have one single image, it will only give you a 2D image, just like when we are getting our chest scan. So it's only one single plane, so we can see the chest from the front. It is not a 3D image. Whenever we did a 3D image, we always need at least two. Minimum is two. We need to have two images from different angles, so that we will then use computer algorithm to combine the two images together to create this 3D image. So in here, you can see that there are actually two devices. You can see that there's a gray X-ray tube and a image intensifier, and this one is in green X-ray tube and image intensifier. We need to collect the data from the two different angles. So you can see that from one image, you will see it on this plane, and from another source, you will see the bone from another plane. And once we have the two planes, then we can use our computer algorithm to combine them together. Because at the end of the day, no matter how well we can do the modeling, like it's still only estimates like where the joints are located, and there's no way for us to know exactly how the bones are moving underneath the skin unless we have the X-ray. And that's why X-ray is still the gold standard method for assessing the body structures with high resolutions. So as I said before, images from two different angles will be used to determine the 3D orientations of the body segment. And this set of images can also be collected at relatively high frequency, like 100 frames per second or 100 hertz. So for normal walking, this is good. But of course, like for sports, like this is nowhere near where we need it. But for sports, a lot of it's very rare that we use this sort of technologies to analyze for sports movement. So this is usually to look at walking and at most running. So this is the videos of what we're actually seeing. So you can see that in here we have two units looking at the bone moving from two different angles. And from here, then we can look at on the video images that you can see on the right side of the screen. You can actually see the hip joint moving in two different angles. And with some medical knowledge, you know that this is not human joint. Like human joint would not look like that. It will not appear black in the image. This is actually a hip replacement surgery. So the person may have suffered a hip fracture, and the doctors decided to do a hip replacement and replace it with a metal alloy joint. So this metal alloy joint is being placed within the femur. So this the faint image that you can see on the back will be the femur of the body. And by inserting this metal alloy joint components, not joint, components within the bone, then it can articulate with the acetabulum joint or the hip joint. And then this type of technologies can then be used to see how well the joint is performing when the person is walking and whether there may be some discomfort. You can see that not only the femur, the head of the femur is being replaced by metal, but also the joint socket is also replaced by metals. As you can see, it appears a very dark color socket that receives the head of the femur. So that and you can also see that, yeah, the other side also has it's also being replaced by metal alloy. So this is a complete hip replacement surgery on the bilateral side of the body. Okay, so we have talked about like different technologies that we can use to capture kinematic data, but those are only kinematic data. Kinematic data is the measurement of the movement of the body. You try to describe the motion. So we are trying to use variables such as the time, the distance or displacement or joint angles, or the velocity data, like how fast is moving, how fast is joint turning, so both linear velocity and angular velocity, and also acceleration data. But so far, we have not talked about force, because a lot of time we need to, in order to understand movement, is the force that is behind the movement. We need to exert some force, and by exerting some force on some mass, then motions will occur. So force is a very important element when we try to analyze sports movement. So the next section of this lecture is going to be focusing on talking about the force sensors, like how do we detect forces in sports. So typically when we talk about forces in sport, a lot of time we are talking about the force that we exert on the floor when we are running or jumping or landing, and we try to analyze how much force we have when we interact with the environment. Because a lot of time when we are interacting with the environment, only our foot is touching the environment, because the rest of the body will be in the air. So that when we ignore the air resistance, then most of the time, the only place that we receive external force would be through the floor. And that's why these sort of force platforms are very popular when we try to analyze forces in sports. So force platforms are electronic devices that are specializing in detecting three-dimensional ground reaction force. So unlike your bathroom scales, when we stand on our bathroom scales, you only detect vertical forces. So you only detect how much you weight in the vertical directions. You will not detect the forces in the forward and backward directions or in the left to right directions. So force platforms can fill those gaps. Not only that, it can replicate what your bathroom scale can. It can obviously tell you how heavy you are, but it can also tell you how much force you are exerting in the two horizontal directions. So when a person walks on it, you can see that the arrow is not only pointing upward, like your bathroom scale. Your bathroom scale only tell you what's the vertical force, but you can see that this arrow is actually moving in the forward and backward directions from this image, but actually it also tells you the forces in the left to right directions, but you just can't tell from this video because this is a 2D video. So you can actually tell the 3D forces that you exert. If you look at this graph carefully, there are actually 3 lines that you can see. You can see that there's one line that's very large. You can see that there's a actually 3 peaks, but you can see mainly 2 peaks. But this is actually one early peak, followed by a second peak, followed by a third peak. This would be the vertical force we exert on the ground when we're walking. You can also see a trace that goes up and down, and that appears to be orangey color. I can't really tell, it's too small. This is actually the forward and backward force that we exert on the floor. So you can see that compared to the vertical force that we exert on the floor is significantly less. So you first start off with a braking force, a force that pushes our body backward, followed by a forward force, pushing our body forward. That's how our body is able to walk forwards. Because when our body exerts a force on the ground, we exert a downward and backward force on the ground. Then the ground, based on Newton's third law, will exert a ground reaction force, which is opposite and have the same magnitude force as the force that we exert on the ground. So it will be a forward, upward, and forward force that push our body forward. And the arrow that you see would be the direction of the ground reaction force. At first, it's pushing back on our body. Actually, it's a braking force. It slows our body down. And then this force will turn to forward directions, pushing our body forward. So that trace that you can see on this curve would be the anterior posterior force, or the forward and backward force in layman term. The very faint line that you see on the back is actually a force that we exert on the ground in the left to right directions. You can see that it's almost zero most of the time. That's true, because most of the time when we're walking forward, there are not lots of force in the middle lateral or the left to right directions, because we are trying to walk forward. We are not trying to turn to the side. But for example, if in sports maneuver, if you are doing some cutting motions, if you want to suddenly move from the center and suddenly turn to the side, then you are going to see a much larger trace that is pushing your body to either the left or right side. Then you will see a much larger line on the back. So a lot of time there will be 4 sensors that are being placed on the corners, and due to the different reading from these 4 sensors, then the force plate will then be able to detect where the center of the force is being placed on the force platform. And this center of pressure is where you can see the origins of this arrow. You can see that the arrows is actually shifting. At first, when we first step on the platform, this arrow actually starts from the heel where we strike the ground. And then this arrow actually moves towards the front of the toe. If you can see more carefully from this image, the arrow base is not fixed, it's actually moving. And that base of the arrow is actually the center of pressure, and the arrow is the direction of the force. So using these sensors, this sensor is actually not just a vertical force sensor, but it's actually a strain gauge that is being able to detect forces not only in vertical directions, but also in the orthogonal directions. So both in forward and backward and left to right directions. So those are the shear forces that it measures. And that's why you can also tell the shear force from the sensors. So this type of force sensing platforms can be used in many different settings. Traditionally, it has been placed on the ground surface. So it, a lot of time in the gauge lab, you can see that this force platform is being placed embedded onto the floor surface, so that you have a level surface to walk or run on. So a lot of time, because you need to have the foot being placed directly on the force plate and not across the edges. So you may need to have multiple force plates so that you can capture the entire running sequence. So sometimes you will see like 2 force plates being placed side by side, and you will have like 8 force plates in total, like 2 side by side, and then you have 4 in sequence, so that you will capture the entire walking pattern. And or else you have need to have very careful placement of the foot when they strike the ground. So sometimes you can place this force platform on top of another platforms. If you want to do like stair walking studies, you can put the entire staircase on the platform to look at the movement. You can even put it on a slender surface to look at the forces when you're walking on a slope, or you can even put it on a treadmill so that you can see how the person is walking and how the force change when the person is moving across a when they're walking on the track. So in comparison, sometimes the force data will only give you a single point, which is the center of pressure, and also what is the direction of the ground reaction force. But sometimes that's not what we are interested in. Sometimes we want to know how the pressure is being distributed along the plantar surface of the foot, or the sole surface, or the bottom surface of the foot. So you can see that this map is actually showing like how the force is being distributed. You can see that a lot of the force will be concentrated under our big toe and under our heel. This is very typical. Like most of the people will have forces concentrated in the forefoot area, in the toes, in the big toe, and also in the heel. So if you want to have data like that, we cannot use the force plate, because force plate will basically take an average of all those forces, and it will tell you where those forces is centralized, and they will give you one single point. It won't tell you whether the force is more concentrated on the heel or toe, or like how it's being distributed. So in order to know the force distribution, we actually need a different technology that is called the plantar pressure, or the pedal biography. So pedal biography will return the distribution of pressure across the bottom surface of the foot. So instead of having 4 strain gauges being placed on the 4 corners of the force plate, for this sort of technologies, they're actually a matrix of sensor being placed. So there are little sensors that's being placed, being distributed evenly all across the surface of this force sensing mat. So when the person walk, basically your individual sensor is going to give a value, because individual sensor is just like a miniature bathroom scale. It is going to detect only the vertical force only. This time it only measures vertical force. It won't detect any shear force or the horizontal forces. So each sensor is going to tell you how much force that it sends. And by combining the readings from all the sensors, then you can get almost like heat map. So where the forces will be centralized. So you can see that when the person is walking, at first the force is being concentrated in the heel, and then gradually the force is shifted forward into the forefoot and then in the toe regions. So you can see similar to the force plate will tell you where the force is centralized, only one single point. But this returns more than just one single point, but you can actually returns the distribution of force all the way around from the heel to the forefoot and to the toe. You can use this barefooted. You can have a barefoot walking on floor, or in some other devices, you can actually tell. You can wear underneath. Within your shoes, between your foot and within your shoe, to tell how the foot pressure is being distributed as you walk around. So you are not limited onto a small surface that you have to step on. You can actually walk anywhere you want. So this type of sensor is actually very good for us to detect foot abnormality. For example, whether the person has high arch. So you can see that this foot has a irregularly high arch, so that is completely off the ground. You can see that there's no force being distributed in the midsection of the in the sole. So this is a regular foot versus a flat foot, so that you can see that the foot is completely flat, and that's is a missing arch. So not only that, it can also be used to look at gout. Gout is when we have basically a crystal deposit in our joint, which will cause tremendous pain in our big toe most of the time. So at that time, when we feel the pain in this area, the person will adjust the gait to help to alleviate the pain. So the walking pattern will be different. So we can look at how the pressure is being distributed to know whether the person is suffering from gout. So these 3D force distributions can be integrated over time, so you can actually see how the force is being distributed over time. This is also very important to analyze diabetic foot ulcers, because depending on the footwear they wear, we can identify what are the stress area underneath the foot. Because for diabetic patients, a lot of time when they suffer any skin ulcers, then this skin ulcer is going to have a very difficult time healing due to their diabetes. So basically, the heel just the wound just lost the ability to recover themselves. So when they have foot ulcers, formation is actually a very dangerous situation for these type of patients. And sometimes they need to amputate their not just the foot, but even the lower leg to save the life, so that the inflammations and will not be affecting the rest of the body. And sometimes we can also use this type of technologies to determine the injury risk, because for sports that have a lot of repetitive footwork, for example, marathon running, if the pressure always exists, or high amount of pressures always exist in some part of the foot, we know that eventually, like that part of foot will either have a skin injury, or even bone or fascious injuries. And that's why we may need to prescribe specially designed insoles to alleviate the pressures, to distribute the pressures over larger areas, so that we can lower the risk of injuries for those athletes. So we can see that by using this type of technologies, we can also see how the load is being distributed. For people who run and have a slight overstride and land on the hill, you can see that the peak force is actually quite high. You can see that this dot will reach almost the top of this line here, meaning that there will be a lot of load onto the hill. So if you run with this type of pattern for a long period of time, sometimes they will have develop heel pain due to this type of running. If the person's run with a forefoot or a midfoot strike, you can see that unlike the image on the top, for the video in the bit below, you can see that the person is running and landing with the mid to forefoot area. You can see that this dot doesn't travel all the way up to the top. Instead, it only travel midway, and then it come back down when the person lift the foot off the ground. The reason for that is because a lot of the force is being absorbed by the Achilles tendon and also the calf muscle, or the gastrocnemius and soleus muscles of the backside of our lower leg. And because of that, the force will not be impacting the heel region, so that the risk of suffering injury to our heel bone will be greatly reduced. But of course, like with this sort of running, the stress will then go to the Achilles tendon. So depending on what is the situation, it may not be the best situation for some of the athletes. So by having a very good measurements of the how the pressure is being distributed and how the pressure is changed over time, we can actually capture how the pressure is being shifted from the heel of our foot to the toe regions. So by having this trace is actually quite useful, because a lot of the footwear, we can actually design for that to provide maximum support to the athlete. For example, if we know this is the trace of the center of pressure, you can see that the bottom of the sports shoes closely resemble this line here. So what does it mean? It means that when the person is running, the pressure is being concentrated in this area. But then you can see that this shoe is cleverly designed. Instead of having this part of the sole pressing on the ground, this part is actually slightly elevated from the ground surface, meaning that when the pressure is being distributed along this line, this force will not hit the ground directly. Instead, when you apply pressure into this region of the sole, because this is not touching the ground, this force is actually being distributed evenly along both sides of the COP line, meaning that the person not only will have less force being received from the ground along this line. Secondly, the person will feel very stable when he or she runs, because this force is evenly distributed on either side of this line, meaning that you are well supported on either side and not just on one side. If you did not design this properly, if this line is falling to only one side of the support, then the person will feel very unstable, because once you land, you'll feel that although one side is well supported, the other side is not well supported, then you are going to fall towards that side. Then you will feel that, oh, every time when I step on this, every time when I strike the floor, I feel that I'm unstable. It feels that I'm falling laterally. Then it means that the shoe design is actually not converting to how your COP is shifting when you're running. So as I said before, the force platform, the limitations would be I need to place my entire foot on the entire surface of the force platform. So if the force platform is here, I need the foot to place directly onto the force platform. I cannot step on the side because once I step on the side, some of the foot will be supported by the floor, some of them will be supported by the force platform, and hence I cannot measure what's the ground reaction force because some of the force that is being placed on the actual floor will not be measured by the force platform. So the old pedal system is also similar. Like if we have a certain platform or a walking mat, then you have to walk on this area because the sensors are only being distributed within this area. Once you step outside of it, we won't have any data. So that's why you can see that there are some PolyU devices, and these sort of devices have the sensors that are being placed onto a device that looks somewhat similar to an insole. So this sort of insoles can be placed directly into our shoe. And if we place this insole into our shoe, then we can walk anywhere and have pressure data. And basically, you can just type your shoes, and everything is portable. The data can be transmitted through wires or nowadays through Wi-Fi or Bluetooth, and then sent to the computer. Then you are not limited to a particular walking surface. You can basically walk anywhere. Not only a flat surface, you can even go hiking or running on uneven surfaces and to look at how the pressure is being distributed over time. So the application of that would be a lot more. But then the traditional sensors are also good because sometimes we can place these sensors on a treadmill, and then we can also track how the pressure is being distributed when the person is walking on a treadmill over time. Okay, so this is a good time to take a second break for this lecture. So we will take another 5 minutes break, and we are going to resume class at 8:28. Thank you very much. Okay, so once again, maybe I will take the opportunity to do the announcement again, just in case you visit earlier. So please be reminded there will be some multiple choice question related to this lecture that will be posted on Blackboard. So after this lecture, please feel free to go to Blackboard and to answer the multiple choice questions. So they are related to the general information that I've been talking about with the different sports technologies that we have been using nowadays. Okay, so let's resume our lecture. So I noticed that there are some questions being posted, and I will try to answer them as soon as I can. So maybe wait until the end of the lecture for the Q&A. Okay, so first, we have some ways to analyze the motion of the body. So we at the first part of this lecture, we talk about some of the common technologies that we use to capture kinematic data from the person, either using marker-based optical-based system or some markerless optical-based systems, or using some electronic devices, for example, the IMUs, or using dual fluoroscopy as in X-rays. And then the next part is we also talk about some common devices that we use to measure forces. But then there are also some other devices that we use to measure muscle physiology, because a lot of time we're interested in how the muscles are contracting and how do we use the muscles to perform different type of movements. So a little bit background about our muscle physiologies. So the muscle is actually the effector of the body, meaning that it needs to receive command from the nervous systems in order to know what time to contract and how much it contracts. So the coordination of the muscle contractions is being instructed by the nervous systems. So a lot of time the instructions may come directly from the brain. So the brain from the frontal cortex, we are going to develop some movement plan. So how we are going to move, and this motor program is then transmitted through the spinal cord, and then through the spinal nerve, and then through the peripheral nerve, and then to the muscles. And then when the muscles receive this signal, and then you then contract at the right time, so that to produce movements. So this type of unit of the motor neuron and the muscles is called the motor unit, and this has many few different components. For example, we have the neuromuscular junctions, or the junctions between the neuron and the muscles. So the neuron actually through the emissions of different type of neurotransmitter. So most of the time acetylcholine, and it's going to transmit the signal from the neuron to the muscles. And when the neurotransmitter combine with the receptors of the muscles, then the muscles will then transmit these signals within itself, and to release the calcium within the muscles, and then to signal the muscle contractions. So when the muscle is sending the signals within the muscles, it actually sends a electrical current within the muscles. And this is exactly the signals that we want to pick up, because without this signal, basically the muscles would remain at a relaxed state and it will not contract. So the signal that we are collecting would be the electrical signals that's being transmitted within the muscles themselves. And the muscles will contract when receive this signal, will shorten, produce force while consuming some energy source, not necessarily oxygen, sometimes oxygen, sometimes just ATP in general. And the equipment that we use to detect muscle contractions would be the most common one would be electromyography, or EMG in short. We can also look at oxygen consumptions, because when we are doing aerobic exercise, then the muscles will be consuming oxygen to create its energy source, or ATP. Or we can detect the muscle force. So first would be EMG, electromyography. So you can see that in these images, the person is wearing a lot of the electrodes on the body. So here you can see that there are two electrodes that are being placed along the axis of the muscles. And these signals will then be transmitted through this wire into this amplifier. This amplifier is not only just going to filter the signal, but it's also going to amplify the signals and then transmit to the receiver of the computer using Bluetooth technologies or radio frequency, or etc. So depending on the different brand, they will use different technologies to transmit these signals back to the computer. So electromyography measure the electrical activities produced by the skeletal muscles using different type of electrodes. So the most common type of electrodes that we use in sports would be surface electrodes. So the surface electrodes, as the previous image showed, we just tape the electrodes directly on the surface. These type of electrodes are actually very similar to the electrodes that we will use in ECG, for example, to detect the electrocardiography, which is the electrical signal of the heart. Those are actually quite similar. And also sometimes we will use a needle electrodes. So basically we will puncture the body using a needle. Sometimes we will need this type of electrodes if we need to detect muscular signals from muscles that are deeper in the body. Because we know that the body is separated into different layers. Sometimes some of the muscles will be running on the surface of the body. Some of the muscles will be running underneath it. For example, in our biceps, we will have the bicep brachii running on the top, but then the brachialis muscles is running underneath the bicep brachii. So if we want to know the muscle activities of the brachialis, it's impossible because if you use surface electrodes, we are always measuring the muscle activities of the bicep brachii and not the underlying muscles. So in order to do that, we actually need to have a needle EMGs to sink into the skin, sink into the muscles, all the way through the bicep brachii into the brachialis muscles in order to detect the muscle activities of those deeper muscles. Of course, like this is not normally done, like because nobody, like especially athletes, like they don't want the body being punctured. This is the invasive method. So this type of study is not often done, but sometimes like in clinical practice, if they need to understand more about some irregular muscle contractions in some deep lying muscles, then they may need to use these type of technologies to use those. So when we collect EMG data, the data we can analyze in both the time domain and frequency domain. So what does that mean? Time domain is we just collect the data, and when the muscle contracts, you can see that the trace will go up. So it has high amplitude, meaning the muscle is being contracted. And then when the muscle relaxes, you can see the signal coming back down. So this is when we just analyze the movement over time, we will see when the muscle is being active and when the muscles turns back off. So this is a time domain. The second way we can look at the signal is looking at the frequency domain. So what does that mean? Frequency domain is actually looking at how fast the signal is moving up and down. So this trace here is already the filter signal, so you don't actually see the muscle signal is actually not that clean. It's not just turning on and turning off. It's not like that. But the signal is actually having a very high frequency signal that goes up and come back down and go back up and go back down. So the frequency is actually we can look at a period of time what frequency signal is actually being collected from the EMG. So typically this is the frequency domain. You can see that the signal will span from around 30 hertz all the way to over 300 hertz, and where we go over 500 hertz. So you will pick around 100 hertz. So that is the median frequency of EMG signal is around 100 hertz. But this is only when the person is at a very fresh state, meaning that they are not tired. But once the person gets tired, the median frequency actually shifts downward. And first it was at 100 hertz and gradually shift to 90, 80, or even lower. The reason for that is you may have heard before, like in the human body, there are two main types of muscle tissues. One is called the fast twitch muscle tissues, and the other is called the slow twitch muscle tissues. The fast twitch muscle tissues, like the name suggests, because they're fast, they have a high frequency. And for slow twitch muscle fibers, they will have slower frequency. So the median frequency would be somewhat the median of the two, so it would be around 100 hertz. But then the fast twitch muscle fibers, the downside to that is, or the good side is, the good thing is, the fast twitch muscle fibers, they can contract very quickly. It means that it can produce high amounts of force in a very short period of time. Not only that, it can produce high amounts of force as well. But the shortcomings of fast twitch muscle fibers is they will get tired very easily. So it can only be continuously stimulated for around a minute. If you continue to stimulate it after a minute, basically it won't respond because it has already wear out its resources. It can no longer contract after a minute. And that's why you have the intermediate fast twitch muscles and the slow twitch muscle fibers to pick up the slack. And because of that, when the fastest muscle fibers stop contracting, then the frequency of the muscles will be lower, because now all the muscles that are being contracted will be the intermediate fastest muscles or the slow twitch muscle fibers, which will have slower frequency. And because of that, the median frequency will be reduced. And that's why we can, from EMG signals, not only we can get the timing of the muscle contractions, but we can also know the condition of the muscles, whether they are tired or not. Another misconception is whether we will get more signals when the person has more muscles. Yes, we know that Bruce Lee has lots of muscle. Like some of the younger audience here may not know Bruce Lee, but Bruce Lee was like one of the biggest action movie stars back in the 70s. So you can see that his muscles compared to, most of you know him, like he's The Rock or Dwayne Johnson. So you can see that like he has obviously a lot more muscle mass. So do you think that like we will get like more muscle contraction signals from Dwayne Howard? From The Rock compared to Bruce Lee? But actually, that's not the case, because the muscle signal depends on many things, not only the amount of muscle contractions, but also how thick is the skin, how much fat is in the skin, and also how well you tape your electrodes. Because the electrodes is placed on the surface of the skin, so it's going to be impeded by many signals. So a lot of time when we collect EMG signals, we actually cannot compare the signal from one person to another. A lot of time we can only compare within the individuals. But then a lot of time, like if we're only collecting data from the individuals, then it means that it's very difficult to generalize what we collect from one individual to another. And that's why in order to normalize the data, we also need to collect what we call the maximum voluntary contractions, or what's the maximum signal that we can collect from a particular muscle group. So before we can analyze the data, we will ask the subject to contract maximally within a certain muscle. And then that will be the 100% contractions. And then when we collect the data afterward, we will know how many percent of that maximal voluntary contractions that the person is contracting. Then I can compare. If, for example, if Bruce Lee is using 80% of the muscles when he's performing 1-inch punch, and if we ask The Rock to do the same movement, will it be 80%, 50%, or 9% of his maximum? Then we will know how efficient the movement is comparing Bruce Lee to The Rock. Another way we can measure muscle physiology is using dynamometer or resistance assessments. That is also a type of force assessment. So dynamometer is basically to measure force output. So this is a very typical device to measure grip strength. So we can measure, for example, isometric contractions. So most of you may be familiar with this device. So basically, we just squeeze on the handle to see how much force we can exert. You can see that the handle is actually locked. So no matter how hard we contract, there's no way for you to pull the white handle all the way to the end range, because it's stuck. You cannot just pull it. So this means that the muscle is undergoing isometric contractions. The muscle is generating force without changing its length. The muscle length is fixed when we are generating force. The other type of muscle contraction is called isotonic contractions, meaning that the muscle length change while producing force, resulting in joint movement. So this is what we are most familiar with. So I'm carrying some weight, I'm contracting, the muscle shorten. So this is concentric contractions. And sometimes I'm holding this weight and I'm elongating the muscles, and that will be eccentric contractions. So the muscle lengthen while contracting. The last type of contraction is called isokinetic contraction. So it is less known to some of you who are not having a sports background. So isokinetic contractions means that the muscle contract with a constant speed. So sometimes it's very difficult to do, because when I contract harder, the joint will move faster. When I contract with less force, then the muscles will contract slower. So how do I fix the speed? I actually need to have another device. So this device will change the amount of resistance, so that depending on so no matter how much force you contract, your knee is going to contract at the same rate. So the speed of contractions will will be fixed. It will not change. So this is isokinetic contractions. We fix the speed of contraction. So different devices will be used for different purposes. So for example, a simple dynamometer can measure the maximal isometric force that we exert, while different devices, we can also measure force. So this one is obviously not an isokinetic device, but an isotonic devices. So we can measure how the force is being changed over time when we do the curl. So different type of devices is used for different purposes, as I said before. So isometric is usually used to detect MVC, maximal voluntary contractions, and isotonic contractions is usually used for strength training and repetitions, whereas isokinetic contractions is often used for recovery monitoring and comparing limb strength. The reason for that is why we need this specialized device is we set what is the speed of contractions, so that usually the patients, when they're recovering from various type of injuries, for example, ACL reconstructions or knee injuries or other type of injuries, then we will be able to set the limit of how fast they can contract, so that they will not overwork and re-aggravate their injuries or to make their injury even worse. Another type of muscle physiological measurements that we can take would be muscle oxygenations. We can use near infrared spectroscopy to measure the amount of oxygen within our blood. So near infrared spectroscopy is a non-invasive way to measure oxygen saturation level. So before this technology comes along, like a lot of time, what we need to do is we actually need to get blood sample every point in time. So the person is running for 5 minutes, you take a blood sample. After 10 minutes, you take another blood sample. And then from the blood sample, then we'll analyze how much oxygen is in the blood. But nowadays, we have a non-invasive way of doing that. So instead of having taking blood sample from the fingertip when the person is running, we can use the NIRS, which is near infrared spectroscopy, to emit a near infrared light with a wavelength range from 700 to 900 nanometers in the tissues. Because the light can actually penetrate through the skin for a certain depth, it can then penetrate the skin and then reflect it back to the detector. And then the detector will be able to detect like what's the wavelength of light that's being bounced back off from the capillaries. Because we know that both hemoglobin or myoglobins, the two proteins responsible for carrying oxygen, both in the bloodstreams and in the muscles, will absorb near infrared light. So if it's carrying a lot of oxygen, then a lot of the near infrared light will be absorbed by the hemoglobins and the myoglobins within this area, and hence the light that bounce back to the transmitter will be low, meaning that we know that a lot of the then we'll know like how much oxygen is being absorbed. So by analyzing the amount of wavelength of the light being absorbed, we'll determine the relative concentration of oxygenated and also deoxygenated hemoglobin and myoglobin in the muscle tissues. So nowadays, you can see that these devices are everywhere, basically in a lot of the sports watches that you can purchase commercially. You can detect your blood oxygen level. So that's the SpO2 or the amount of saturated oxygen blood in the bloodstreams. So all these devices will have the following components. You have the light emission component. So you will see the red light or infrared light emitters from underneath the watch. And this will be absorbed differently by oxygenated and deoxygenated hemoglobins and myoglobins. And then it also has the detector. So you can see that there are also some detectors that are not illuminated underneath the watch. So this will analyze the change in light intensity to know the oxygenated rate. So during repetitive muscle activity, the percentage of oxygenated hemoglobin decrease while the deoxygenated hemoglobin increase as the muscle work harder. So you can see that the blood saturation level will change with sports, and that's how we will know whether the muscles will getting into a fatigue state. So unlike EMG, we need to do the frequency, the Fourier transform to look at the frequency domain data to know whether the muscle is fatigued. Here we have an alternative way to look at the oxygen in the blood content. The next way to analyze muscle physiology is through computational modeling. So, so far we have talked about using motion capture systems to detect the movement of the body. Sometimes we'll use different AI technologies to put the bones back into places, but then it's still not comprehensive, because a lot of time we may want to know what are the individual contributions of the muscles or the ligaments, etc., to analyze whether I change a particular sports technique, what will be the impact to the rest of the body. Sometimes we want to do a more detailed analysis of the forces distributions within the body to see, for example, like a very famous athlete was Yao Ming. So he suffered a stress fracture to the navicular bone, which is this piece of bone right here, and not only one time, but the second time, and then he cannot recover from it. So if we really want to understand like why this type of fracture happened, like it's impossible to do it with just placing some markers on the surface of the body. And even with the X-ray technologies, we can only see the bone, like how the bone moves, but you will not see the forces within the bone. So we actually need to use different type of modeling to understand like how the force is being distributed within the bones. So that's why we need to have different computational modeling to actually understand how the forces impact the inner structures of the body. So this is the most basic type of biomechanical model. So this type of models is usually used using different type of motion capture systems. So by knowing the joint centers, basically we can place the limb segments back. And for this type of model, we usually assume that the limb segments are rigid. So we use a rigid body model to analyze the forces within the joints. So to do that, we will use in conjunction with the force plate, because we need to have some force input to the systems. And this force input can only be obtained through the force plate, because when the body is moving in the environment, if the body is not touching any external objects, then the only where it is receiving force would be through the floor. That's why we only need the force plate to understand the external force being placed on the body. And from here, we can then work from segment to segment. We can, when we know the force that is being placed on the foot, then we will know what will be the impact of this force onto the ankle. And once we know what's the forces in the ankle, then we can calculate what will be the forces in the knee. So this process is called inverse dynamic, like how we translate from external forces into internal forces through different joints. But of course, with this method, there are lots of assumptions. The first one will be we have to assume that the body is a rigid body, meaning that all the segments are rigid and they do not deform under stress. But of course, that's not true. But that is the assumption that we need to make when we use this type of mechanical model. And second is because for this type of analysis, we need to know the limb segment length. And limb segment length we can have using the joint center data from the kinematic model. But also we also need the individual segment weight and where the center of mass of this weight is located in each segment. And for that, we cannot measure it, because in order to measure that accurately, we actually need to segment different body parts. We actually need to cut off different body parts to measure it physically. So in order to estimate that, there are some anthropometric data that we can use to measure approximately where the center of mass will be located for different joint segments. And then using those data, then we can measure the joint forces more accurately. So to use this type of model, we need to have accurate marker attachment. And from this marker attachment, we will then use a computational model to find out where the joint centers will be. And then we can link up the joint center using rigid body, and then using anthropometric data to find the center of mass location and also how much each segment weight. and then we can use inverse kinematic. And then we will use the kinematic data that we collect from the motion capture systems, and then use inverse dynamic to calculate the forces within. But this forces is once again a very crude force. You only measure one single force, which is the joint reaction force, and also a collective force. How much force all the muscles around these joints need to produce in order to create this movement. So there's only one single muscle force and one single joint force. But we do not know how this force is being distributed, and we do not know what is the contributions of individual muscles from this total muscle force. And that's why we need to use a musculoskeletal model, which is a multi-body dynamic model, to compute what will be the contributions of individual muscles when we need to perform a particular movement. So we already learned what is a biomechanical model. So now we need to have a musculoskeletal model and to combine together to form what we want in the next part. So here you can see that instead of having a stick man figure, now we can see that this model will consist of real human bones with real human muscles. And then we are trying to look at how the individual muscles are contributing to the joint force. So we know that the joint force is actually a combination of all the individual muscle force. So FM1 would be the muscle one's force, FM2 is the second muscle force, FM3 is the third muscle force, etc., etc. And there are n number of muscles within this joint. And then we can also look at how each muscles contribute to the movement of the joint. So each of the muscles, we know that is attached to a certain distance away from the joint center based on the human muscle model. So we multiply this force by the individual moment arm to calculate what is the resultant joint moment. But then the muscle force is actually dependent on many different things. It's dependent on the muscle length. It's dependent on how fast the muscle is contracting, because from muscle physiology, we know that muscle force is dependent on not only the length, but also the contraction velocity. And also, we also need to be aware of the passive components, because around the muscles, there are lots of passive soft tissues, for example, the ligaments and also the tendons, etc. So we also need to include those passive components. And also, we also need to know what is the maximum muscle force and how many % of this muscle force is being recruited to perform this particular movement. But then a lot of time we can estimate the amount of muscle activation percentage from EMG, as I said before, because we can know the maximal muscle contractions through isometric contractions. So we know what is the maximum, and then from the EMG signal, we know how many % of the muscles are being active at a particular point in time. But then there are still a lot of unknowns in this formula, and there are more unknowns than known informations. And if we have more unknown than known informations, basically this equation is unsolvable. So we need to make some assumptions. The assumption that biomechanists will do is we assume that there's a least sum of muscle activations, meaning that our body, being a very efficient machine, you can call this a machine. This machine is a very efficient machine, meaning that it tries to minimize the amount of energy we spend to perform a particular movement, because the central nervous system is actually programmed at a very young age to contract only the bare minimum of muscles to perform a particular movement. It doesn't want to expand energies into waste to produce the same movement. And because to produce the same movement, there are many ways to produce this movement. You can contract muscle A by 100%, muscle B by 50%, muscle C by 10%. Or we can contract muscle A by 50%, muscle B by 60%, and muscle C by 20%. So all of these different muscle programs can produce the same movement. But how do we select which movement is actually used? Is we assume that the least amount of energy it will be used. And then if we can compute that, then that will be the variables that we will use for this model. So this model uses the least metabolic energy consumptions to produce the same amount of force. So this is the assumptions that we make. And according to many different research, this is actually hold up generally true in most of the scenarios. Like our body will try to conserve energy and use the movement pattern that use the least amount of energy. So we can use this type of model to know the muscle contributions in different activities. For example, in walking or in running, that we can see the amount of muscle exertions, how it changes. So blue is minimally contracting and red is more actively contributing, so that we can see the timing of different muscle contractions in different situations in walking versus in running. So that is still not sufficient sometimes, because that will only tell us what is the individual muscle contractions at a given point in time in muscles. But what if I want to analyze injury? Like, why do stress fracture happen to the navicular bone and not in the calcaneus, and not in the talus, and not in the cuneiform? Like, why does it happen to the navicular? Like, what is happening? Like, is there anything that I can do to minimize this stress? In order to do that, we actually need to move in the next type of model, which is called the finite element model. So finite element model, as you can see that we divide the body into different elements, meaning that each individual segment is a individual element. And then we will know the relationship from element to, from node to node, basically. So we will know, because we know what type of structure this is. In this case here, you can see in this image, they are metal. Then we know how the metal behavior, we know the metal behavior and what is the mechanical properties of the metal. Then we can input all this information into the computation model to calculate where the stress will locate. For example, for this particular object, the stress would be concentrated in the joint region here and also around this opening here. And when a beam is being twisted, you can see that most of the stress will be placed at the end of this beam and not at the base. So using this type of information, then we can analyze how the stress is being distributed into different areas of the model. So now looking at the human model. So because we know that the human is made up of different parts. For example, we have the skin. Underneath the skin, we have muscles or ligaments or fat and different type of tissues. At the bottom of the foot, we have the fascias. And then you can see that there are many lines symbolizing there are many ligaments and tendons underneath the foot. So each of these components or the elements, we have some data from, because from dissecting cadaver studies, we can extract different tissues, and then we can look at the mechanical properties of all the different type of tissues. And by inputting all these tissue property data into the model, then we can model like how the force is being transmitted from the skin into the bone, and how this force will be absorbed by different areas. And you can see that when the person is walking, the force is transmitted from the toe regions and then through the metatarsal bone, through the cuneiform, and enter to the navicular bone. Navicular bone is the bone in front of the talus and the calcaneus. So this bone here is actually under a lot of stress when we are lifting our foot. So, and that's why, like, we can explain like why does the injury happen to this particular bone and not the others. And also, not only by knowing this, we can also model, can we change the footwear design, or can we put some insoles underneath the foot by adding this type of layer? Can we change the loading pattern, and whether we can minimize the torque being experienced by a certain stress area to minimize the injury risk of the person. And then moving on next, because now we are moving into the age of AI or Gen AI. So there are lots of machine learning models that we can also use to analyze this type of sports data. So I'm not sure whether you're familiar with AI or machine learning. So machine learning is actually a subset of AI. This is actually a more primitive form of AI. So after machine learning, we have deep learning, and now we have the Gen AI. So in machine learning, this actually depends on a lot on the human input at this stage. So at first, we need to clean up the data so that the data is standardized. We will try to remove all the outliers. We will try to fill in the missing data. We will try to standardize all the units, because sometimes some people, they measure the data in kilograms, and sometimes in pounds, and sometimes in meters, and sometimes in feet. We need to normalize all those data in the data cleaning sections. We need to take care of all the missing data. We need to take care of all the all the outlying variables, because that can have a detrimental effect of our model outputs at the end. So we need to clean up the data first. And then after that, we also need to select some features, so that because when we collect the data, usually there are too many redundancy, and there are too many data. So if we need to include every single piece of detail for the computer to learn, usually it is going to take forever, and sometimes the model may not be optimized. And that's why based on some previous research or some of our previous knowledge, we need to select the most important features that we want to focus on. And then we'll then do some hyperparameter tunings to make sure that our model will be optimized, so that we'll, for example, we'll choose the number of layers within the machine learning model, etc. So we'll set different type of hyperparameters, and then we'll then train the models using the data we have. After that, we will test the model to see how well the model performs. If the model is performing satisfactory, then we will have a AI model produced. So there are different ways that we can train the model. A lot of time when we have a fixed data set, we will use a portion of it for data training, for model training, and a portion of it for testing. But then it's also possible to use all your data to training, and then use someone else's data to test. That is actually even more reliable. So this type of machine learning model can be used in many different areas of sports. For example, we can use for technical analysis. A lot of time, we will have a lot of different sports statistics. For example, this is first come famous in baseball, in Major League Baseball in the US. Because in baseball, it's a relatively simpler game compared to a lot of games. The interaction is usually between the pitcher. The pitcher will throw the ball, and then the batter will try to hit the ball. And then depending how the batter hit, then we have people on the defensive end trying to catch the ball and then throw the ball to the right area to get it out. So the interaction between players is actually minimized, so that the computational model is actually relatively simpler. And hence, they can use this type of model to predict how trading away a player or trading a player to come join your team will affect your team dynamic. So that's why they have a very famous book that's being published called Moneyball. So they use the minimum amount of money to buy players that may not be very productive on another team, but he or she, for Major League Baseball, or he, or how the baseball player, when they join your team, will have the greatest effect on the overall team performance. So they will find what's the most cost-effective way to recruit the players to contribute to the team success. Another major applications of this type of model is for injury preventions. So a lot of times they will collect a lot of epidemiologic data. So like how different factors will affect the injuries. For example, gender, age, the type of sports they play, how much they're playing per week, what's the training intensity, etc. Like they have all this data. And by having all this data, they will then predict like what is the chance of injury of this particular athlete. So by having the injury model, you will also help the trainers or the coaches to make good decisions for their athletes to minimize their chance of injury, so that they can stay healthy in the game and postpone retirement. And that's why, like, if you compare like athletes from nowadays to the old days, like nowadays, like the athletes, like they usually can stay healthy and active for a long period of time. Like LeBron James, for example, he's playing until like he's in 40s, and he's still performing very well because all this new scientific knowledge of sports, so that he can maintain a good training schedule and to maintain their the load. Of course, like for NBA fans, it's not always the best news when they hear the term load management, because load management is the player trying to schedule their own rest period during the game season, so that they can prolong their playing career, and also to keep themselves fresh for the playoffs when the games are more important. So this is like, how do they have this data? Is through the injury prediction model, and that's why this is now being used in a lot of the professional sports arena. And also another major area is being used will be in talent identifications. So based on various performance matrix. So for example, they will collect some basic information. For example, your highest jumping height, your running speed for different distances. For example, for short sprints, for 100 meters, for 200 meters, etc. And based on some basic measurements of the human body, like your height, your shoulder width, your arm span, etc., or your trunk length, your leg length, your Achilles tendons length. So all of those information, you can put them into the model, and then it will tell you that, oh, this particular persons will have the highest chance of success in a particular sport, because it fits the criteria of the most elite athletes in this sport. And hence and this type of systems can then be used to identify talent, and then the society can then invest resources into training the athletes to become an elite in that particular area. So there are also some other general physiology monitoring measurements that we can use to measure different fitness levels, for example. So one is for gas exchange, we can use a metabolic cart to measure the amount of oxygen that the athlete inhale, and how much carbon dioxide that he or she exhale. And then we will know the energy expenditures. So this is known as the VO2, or the volume of oxygen. Usually there's a dot on top. So instead of VO2, it's a VO2 with a dot on top, because this is usually the rate of oxygen, not just the amount of oxygen, but the rate of oxygen uptake that is actually being analyzed. So a breathing apparatus is connected to a metabolic cart to analyze the amounts of the differences of the gas compositions between the air that you breathe in and the air that you breathe out. So that using different type of information, then we can calculate how well the body is using, or how much oxygen the person is using, and how well the person is using oxygen to perform different movements. So for example, like by looking at the respiratory exchange ratio, the RER, or the ratios of CO2 produced to the O2 consumed, we can know at what state the person is in the sports performance. For example, if RER is around 0.7, we know that person is burning fat. Or when RER is around 1, the person is using carbohydrate in the metabolisms. Whereas when the RER is greater than 1, it means the person is using anaerobic metabolism. So this is, of course, like only during high intensity exercise. For example, during HIIT, we are using a lot of anaerobic metabolisms. So by looking at the oxygen consumptions, then we will know at which stage we are. For example, whether we are using completely anaerobic, using ATP that are stored previously for producing energy, or we are using ATP PC or creatine to produce the energy, or whether we are using the lactic acid systems, or whether we are using the aerobic systems, or whether, this is the overall physical activity. So we can be using different type of metabolic systems to produce our energies. So for example, like when we are doing short distance running, for example, 100-meter sprint, you can see that most of the energy come from ATP PC, and a significant portions come from lactic, and very small portions come from aerobic. But then you can see the proportion will be shifted from ATP PC all the way to aerobic. For example, in marathon, almost 8%, almost close to 100%. So going to 10,000 meters, most of them will be aerobic. But then if you go to in the marathon, not only that 80% is in aerobic, 20% is in triglycerides. So you have even burning fat for your to obtain enough energy to complete the marathon running. Another thing that we can monitor is, of course, our heart rate. So heart rate is also a good way to measure like how much exertion that we're doing, because we know that heart rate is also closely related to our VO2 rate. So by having the correct heart rate, we know that how much exertion the athlete is investing. So normally, if we want to have a the threshold or the tempo zone, this zone of training is actually preferred, because this is actually going to help train our lactic threshold and also our race pace. And this will training at this pace will also improve our VO2. So this roughly translates to around 80 to 90% of our max heart rate. So if we during our training, if we can hit this target during our training, usually that will be preferred. Unlike the other regions, when it's below 80%, usually it's too light, and when it's over 90, it's too high. Basically, you are just burning your ATP-PC and also rely almost entirely on anaerobic capacity. And lactic acid will build up very quickly, and basically you cannot continue training for a long period of time. That's why we want to hit zone 4 most of the time in training. So in order to measure our heart rate, usually we'll use different type of heart rate monitor. For example, the most common one would be a heart rate chest strap. So this basically collect the electrical signals from heart contractions. So this will be the most accurate. This will be more accurate than all the sports watches that you wear that basically use a LED or a light emitting dial to detect the blood flow through the capillary. So this is not as accurate because there are lots of variations depending on where you wear the watch, also how well it makes the skin contact, and also what is on top of your skin, whether the skin is clean, whether it's wet, whether you are sweating or not, is also going to affect the reading. So that's why this type of technology still has some limitations. It's not going to produce as accurate data as the heart rate chest strap. And the last, and actually not very commonly used, but still someone will use this, is the heat map. So heat map is the thermography. So thermography is basically used to detect like the temperature that body emits from different parts of the body. So you can see that at the baseline state, the person produces some heat around the chest area and not really in the leg regions. But then during different type of strength exercise, the heat map is going to show distinct features. For example, in strength training, a lot of heat will be in the arms because the person is training the arms. And during training, you can see that the heat is more distributed, not only in arms, also in the legs and also in the face. And for speed training, you can see that the heat area is also not as apparent as the other. In fact, it's actually lower than at the baseline. What is interesting is actually after exercise, the 8 hours after the exercise, the heat map show that the body is actually hotter or more active than even at the baseline. The reason for that is after sports, our body actually needs a lot of metabolisms to recover from all the previous exertions. So the body needs to work very hard to replenish all the used ATP. So there's a very high metabolic rate to restore the ATP to pre-exercise state. And that's why you can see the heat map is actually even higher 8 hours after exercise than during exercise or before you exercise. And you can use the heat map to see like which part of the body is exerting more during a particular sports. For example, this is in badminton playing. You can see that comparing the two arms, it's very obvious that the athlete's right arm is a lot hotter. You can see that the heat map is at the white state, so you can see that you can even see all the blood vessels that is very hot. It's carrying all the nutrients to the arms during this exercise. You can also use heat maps in looking at multiple people as well. So one of the last part would be to look at sweat. So now a lot of the microsensors are being developed to detect sweat or other excretion from the body. For example, we can analyze sweat, we can analyze our saliva. So these are part of the new wearable technologies that are coming into sports. So sometimes this comes in the form of a tape that we can tape on top of surface. Sometimes it can even be included into the textile. So there are some smart textile that harness the technological advances of wearable devices. So these type of devices can be placed within the fabric itself to detect different biomarkers such as electrolytes, lactate, glucose, or pH level from sweat. So different type of it won't be like this. It won't be this big. In the future, it's a very small microchip that can already analyze the sweat content and then to inform the athlete like what is their physiological state while training. So you can see that these type of sensors are very sensitive. You can basically sense the amount of lactate during exercise, and then you increase with exercise intensity, and then during recovery, the amount of lactate within the sweat will also reduce, so that it is a good device for us to monitor our training, and it's a good wearable technologies that is coming into the field. So in future, basically, as I said before, like a lot of these devices and sensors are rapidly changing the sports horizon. So basically, back in the old days, a lot of time, coaches will basically just use their own subjective observations to make judgments. But nowadays, a lot of time we rely on a lot of science and technologies, and advances in different sensors and measuring technologies is transforming the sports and allowing the athletes to perform at a much higher level. But then the next wave of change is coming in the form of AI and also in the form of robotics. So a lot of time we will so we now have a lot of different devices to measure different parameters from our body. But how do we use this data is still up to the questions, because a lot of time each of the device only measure one specific piece of information. But if we can feed all those information into AI, if we have the right AI model, we can then use this type of model to inform athletes or even coaches, like what would be the most appropriate training program for that individuals. Even for not for professional athletes, but even for the individuals like us, maybe we can use these technologies when the sensors become cheaper, and then when the AI technologies becomes more mature, maybe we can just wear a simple watch, and then from this watch, then we can already detect our SpO2, our blood oxygen level. We can detect our sweat, and we can analyze our movements, etc. So we can combine all the features that we talk about, at least part of the different features that we talk about, into a very compact and wearable sensors that we can use on a watch, or even embedded within our clothes. And then we have all this data, and then the AI model can then tell us what is our current status and how should we proceed. Like if I want to improve our fitness, or if I have a very specific target, if I want to train up my muscles, if I want to look like The Rock, if I want to have good strong muscles, what should I do? Maybe AI can, based on my current status, to prescribe very personalized training program for me. And also with the advances in robotics, also a lot of time, like we can train with virtual athletes. But virtual athletes, like you don't have the tactile feedback. So if we train with a robotic athlete, then the feedback may be different, and then we may even have a greater training effect if we are training with robots than training in a virtual environment. So there are lots of different areas that is advancing very quickly, and I'm sure that even maybe next year or in a couple of years, when I give this same lecture, like some of the materials is already completely changed, and then I need to update my lecture notes again to accommodate the newer technologies. So it's a very exciting time, and next week we are going to be talking about running and the technologies in running. So thank you very much for your attention. So this lecture is a general overview of all the new technological advances in different sports technologies area. So if you have any questions, please feel free to put into the Q&A box, and then when I have time, I'm going to reply to your answers. So once again, don't forget, you will need to do the MCQ questions posted on Blackboard. So after this lecture, I can't remember, I think you have until the end of today, like 11:59 p.m. to finish your assessment. So thank you very much, and hopefully you have learned something new today.